will the Casimir variance and the Dynkin indices. So we have noted that representations of simple algebra of rank n are characterized by n positive or zero integers. Okay. So the indices of these are basically constituting your the Dynkin indices of its highest weight state. So now there are other ways to specify these representations in terms of the n operators constructed out of the generator called the Casimir operators. Okay. So you have heard of all the Casimir operators in the context of Lorentz group, as well as when you talk about the angular momentum and so on. And that like in angular momentum you have this J1, J2, J3, and then you construct something called the J square, which is J1 square plus J2 square plus J3 square, and that gives you an invariant quantum number, a good quantum number. Using that you can characterize your state, which is J, okay, and J square commutes with all the upwards. So you're familiar with the word like Casimir operators. Okay. So here the concept is very similar. The Casimir operators that commute with all the generators of the Lie algebra. Now, Lie algebra always have one quadratic Casimir element, but the degree of the higher the Casimir invariance depends on the algebra. So, working on the quadratic Casimir, if you have generators like CA in some representation R, then you can define CR2, which is like TA, or you can think of like a trace of TA when you think about this TA to be the matrix form. So this form we are all familiar with. But the question is that is there the only Casimir operator that one can define for a given algebra or not? The thing is, for SUN, there are n-1 Casimir invariants which are polynomial in TA. So you can connect this n-1 number. That for SUN, the rank is n-1. So for a given group, if you have the rank is n-1, you will have that many Casimir invariants. So now let's consider the algebra A2, which is basically SU3. So where we have two quantities, trace of TATB and trace of TATB TC. So you can see the one is called the quadratic, one is called the cubic. So since there is only one invariant tensor with two adjoint indices, we say trace of TATB equal to IR2 delta A, because these generators are basically orthogonal to each other. And this IR2 is the quadratic Dynkin index of the representation, which is basically r-dimensional representation. Right? Now one can compute the trace of the cube, which can be split into an antisymmetric tensor, which is nothing but the structure function at ABC. And while the total symmetric part is written as trace of TATB TC symmetric as DABC IR3. The antisymmetric part will give you the FABC, that's the constant, the symmetric part will give you the DABC IR3. And this IR3 is the cubic Dynkin index, and DABC is the third rank tensor made of the structure constant. Okay, so this is another Casimir invariant. So you can see for SU3 rank is 2. So we have this IR2 and IR3, these two Casimir invariants. Now suppose that A are the matrices in adjoint representation, then DABC you can write it down as a FAM, FBNP, and FCPM. So such that all the indices are basically like M, N, and P. They are actually summed over. Okay, so they are normalized such that I is equal to 1 for the adjoint. This is a choice of normalization how to do this thing. The important part is that this cubic Casimir is basically product of this structure constant. Now the cubic invariant exists only for those algebras with the property that the symmetric product of its adjoint contains the adjoint. So let's say for any such algebra, the adjoint representation is basically let's say D, and then D cross D if you compute. And you look into the symmetric product of this, so D cross the symmetric part if you compute, and then it contains another D. Okay, so then for them only a cubic invariance will exist. And this is true only for the SUN where n is greater than equal to 3. All those algebra like SU3, SU4, SU5, and so on. Now to relate the quadratic Dynkin index to the quadratic Casimir operator, take the trace over AB. So what you can do actually, I2 delta AA equal trace of TATA. This is like a CR2 trace of identity, and this is like CR2 and trace of identity is basically give you the DR, okay, in which representation you are working on, okay, and these are related to each other by the IR2 as DR by capital D CR2. So CR2 is the basically about the trace of this part, and this is the quadratic Dynkin index. So where D is the dimension of the algebra, and this formula will be very useful when you calculate the beta functions of the gauge couplings, which can be deduced in terms of their representation only without completing the diagram. So these kind of invariants are very useful in the loop calculation. Okay, so if you know these representations and these Casimir, all those structures, so then even you can represent the Feynman diagram, the output of the Feynman diagram in terms of this invariant. So now similarly, CA1 to up to this AK, one can write down trace TA1 up to this TAK, and is an invariant case degree Dynkin indices. So in general, a rank n Lie algebra has n independent invariants which are polynomial in general. Okay, so this is the general remark that we have noticed here. Now for the simple Lie algebra, the order of the polynomial are as follows. For example, if you consider this AN, so then TATB or TATBTC, this definitely is order of T squared T cubed after this Tn plus 1, they are basically invariant. So for Bn, they are very restricted, and you consider like T squared T4 T6 T to the power n minus 1 and so on. And same order of for Cn, Dn, exceptional group like G2, F4, E6, E7, E8, and so on. And this completes the list. Now, the irreducible representations of most of the Lie algebra can be further characterized by a congruence number. So what is this congruence number? This is like an additive under Kronecker product, modulo and integer specified for each Lie algebra. So also we can define the Chang number of a representation which is equal to its dimension mod h plus 1, where h is the question number, and this question number is defined as half L adjoint plus 1, and L adjoint is the height of the adjoint representation. Example, this is 6 for SU4. Okay, so when you talk about the adjoint representation, if you remember the weight 3, if you start with the highest weight representation of the fundamental representation or any representation, and then you subtract the alpha I subsequently, and continue doing that thing as long as you can do for such that it cannot be further reduced in this particular form. All the entries are basically negative or 0 till then you do that thing and then count the height of that thing, and that is the height. Right? So if you start with the adjoint representation, highest weight representation, and then you can deduct this alpha in a similar way for the 6, that is the height is 6. Okay, this is very similar to the previous example where we talk about the fundamental representation, 6 dimensional representation, and so on. Okay, so these are basically related to each other. And the dimension of the algebra is also defined as a rank of the algebra and of the question number of the algebra plus 1, so it is equal to R into H plus 1. So if you know one of two of them, then you can deduce the other one. So now there's another interesting aspect we want to discuss, which is the graphical representation, and which is known as the bar chart. This has been developed by Stanley, and there's a book called the bar chart by him. Okay, so in this Stanley book, we represent and these different kind of invariants or the identities by some kind of diagrammatic technique to visualize this. For example, like we assign state of an arbitrary d-dimensional representation a solid propagator line with labels A, B, and from 1 to D. Okay, and then special state is given to the adjoint representation. Special is given to the adjoint representation in the form of a dotted line. In this language, we associate a propagator line to the Kronecker delta AB and capital delta AB. So this is like an adjoint thing. So this is transform dotted, and this is for the d-dimensional representation. So that transform small AB. So this is solid line. Now, when you represent something the closing line, it implies that the same as summing over the indices, so that the solid circle is D and the dimension of the representation. So there's no other free index, so we just put it like in the closed line. The representation matrices in the d-dimensional representation are depicted as follows. We have a solid line and you have a dotted line. So this is like a TA AB. So you can see that for small indices you have a solid line, and this A it is a dotted line, which is the adjoint one. Now tracelessness of these matrices is then shown as you have a circle, and then a dotted line. This is equal to 0. The second Dynkin index of the representation R is then represented by you have a dotted line, you have a solid line, you have a dotted line. This is like a in the Feynman diagram, the way we constructed this thing. This is another way of defining the representation. And this makes it easy to develop a way to generate the quadratic Dynkin indices for any representation using the Kronecker product. Label the reducible representations R across S by two solid lines, like this is R, this is S. And compute this quadratic Dynkin index, the sum of the quadratic indices of the universal representations in R across S. So since the representation matrices are traceless, they connect to the lines in pairs and leading to the sum of the following diagram. So this is S, this is R, you have this solid line, and then you have this R, this is S, and they are basically connected to each other. This can be written as I R cross S quadratic invariant, Casimir invariant. This is written as a DS IR2 plus DR IS2. Okay, so when your R equal to S, then we can specialize the rule and diagrammatically by considering symmetric and antisymmetric products in terms of the line. So this is the symmetric part, and this is the antisymmetric part on the negative side. So this is the way of product, rewriting this part. So then that will be reduced to the fact that IR2 RR symmetric and antisymmetric is DR plus minus 2. The plus sign for symmetric, minus sign for antisymmetric, DR plus minus 2 IR2. Similarly, cubic Dynkin index is represented as solid circle, and you have 3 lines. Okay, and that you write it down in the same way, like DSIR3 plus DRIS3, and R equal R S are same. So then IR cross R3, symmetric part is DR plus 4, and antisymmetric is DR minus 4, IR3. So this is just a way of looking this thing, but may not be immediately useful, or we may not use this thing, but this is a sidewise comment. So which, if you're interested further, then you can consult this Zizanovic book. Okay, the group theory and the bar set. So now another important aspect which will be useful mostly when we talk about the unified theory, that's called the embedding. The embedding means basically how to embed small Lie algebras into the bigger ones. For example, like if you have a bigger algebra containing SON, and it contains SON minus 1. Now there are two basic rules of embedding. Assume that G contains 8, and the adjoint representation of G contains the adjoint representation of 8, and the smallest representation of G is the sum of non-trivial representations. These two things must be satisfied. Okay, and then we'll see gradually different kind of examples. For example, let's consider the SU3. So there exists only one simple algebra smaller than SU3, which is basically SU2, which is homomorphic to SU3 of dimension 3. And one simple and one semi-simple algebra one can think of rather SU2 cross SU2 of dimension 6. Now let's consider the defining representation of SU3 to be the 3. Note that SU2 cross SU2 cannot be accommodated in 3, as the smallest representation is 2, 1 plus 1, 2 or 2, 2. That's like a bi-doublet kind of thing, which is 4-dimensional. Thus, we are left with two choices. So for example, for SU2, we can write it down 3 as a 2 plus 1, or for SU3, we can write it down as 3 equal to 3. Now, if you focus on the SU2 sector, then you say that 3 plus C1 is 2 plus 1 plus 2 plus 1. And from there, if we remove, we get the adjoint of SU3, which is 8, which is 3 plus 2 plus 2 plus 1. So now, as you know, if this has to be correctly embedded, then this must contain a SU2 adjoint. So this is the SU2 adjoint. So this is SU2 must be embedded in the SU3. But on top of that, there's a SU2 singlet. Okay, so this signifies that there will be some E1 abelian algebra, and that's why the correct embedding would be SU3 contains SU2 cross E1. And these E1 charges can be assigned to the members of SU3 triplet as long as they sum up to 0. And that's the way, like a traceless condition, like 3 equal to 2 minus 1 plus 1, 2. So similarly, from there you can construct the 8 as 3, 0 plus 2 plus 3, 2 minus 3, 1, 0. And the subscripts are basically the E1 charges, and they are not normalized as of now. So the charge of the triplet is 0, otherwise the E1 would not be commuting with the SU2. Right? So if the charges are, it's not a traceless condition, then the E1 generator and SU2 generator may not commute. But this would be, because otherwise you cannot write it down as a SU2 cross E1 format. So now there's another choice is basically think out in terms of the SO3 embedding. So there the 3 equal to 3, so 3 cross 3 was basically 3 cross 3. For SO3, 3 cross 3 is 3 plus 5 plus 1. So now 8 is basically 3 plus 5. Now you can see that there is no SO3 singlet, which ensures the absence of E1. So that's why the SO3 is only embedded in the SO3. There is no accompanying E1 unlike the previous one. Okay. So this way the branching actually tells you what kind of allowed embeddings are there. Now let's talk about some more non-trivial structure, okay, which will help us to explore different possibilities. Let's talk about the SO8. So it is a rank 4 and it has 3 real octets, which are defined as 8i, where i can be D vector or S and S prime, there's 2 real spinors. Now the adjoint representation is 28 as 8 cross 8 is 28. Okay, it's like an antisymmetric product. A possible choices of embeddings could be in terms of the representations of algebras of rank less than equal to 4. So what are the possible algebras like SU2, SO3 or SP2, or SU3, SU4, which is homomorphic to SO6, or SO5, homomorphic to SP4, SC is the symplectic group, and then you have SO7, SP6, and G2. So these are the possible. So you might be wondering that why not SU5? So SU5 also has rank 4. This is a mistake here. This is rank 4. So this would be like, the condition satisfying and less than equal to 4. And its lowest dimension representation is 5, which is complex. But since HV is a real representation, this must contain either real representation or complex representation accompanied by its conjugative. Then it can be accommodated in the real representation. Right? But 8V cannot contain 5 plus 5 bar, and because it's a 10-dimensional representation. So thus SU5 is not a good choice and cannot be embedded within this SO8. Now 8 can be partitioned into the largest integers as 8 equal to 8 plus 0, 7 plus 1, 6 plus 2, 5 plus 3, and 4 plus 2. These are all independent structures. Now the task is to identify these integers and partitioned integers in terms of the representation of some subalgebras. Let's start with 8 equal to 8. So the 2 possible subalgebras are there. So 8 is known as the adjoint of SU3, which is the octet. Okay. So SO8 contains your SU3. Then 8V equal to 8. So 28 would be 8 plus 10 plus 10 bar. Right. Now you can see that adjoint of SO8 contains the adjoint of SU3. So this is the correct embedding. And for the SO7 spinor also, there is a representation 8. 8V equal to 8, but the 28 is 21 plus 7. Right. So that's why SO7 also can be part of this SO8 or can be contained in the SO8. Now 8 equal to 7 plus 1. So SO7 also has a 7-dimensional representation. Okay, so SO8 contains SO7, then 8 equal to 7 plus 1, 28 equal to 21 plus 7, that we have already cross-checked. This is a valid embedding. But 8 equal to 7 plus 1 partition is not the only way to look into SO7, but in terms of the G2 also. because G2 has a represents 7 dimensions. So SO8 can be possibly containing a G2. So then 8 equal to 7 plus 1. So 28 would be 14 plus 7 plus 7. Okay. And more interestingly, here the SO8 actually contains SO7 cross G2. Okay. So now next partition is 6 plus 2. So if you write down 8 as 6 plus 2 or like 6, 1 plus 1 plus 2, then 6 can be of SO6 and 2 can be of SO2 in the primary notion. So interestingly here, you can see that for 28, it's like it contains the adjoint of SU4, like because this is 28 is the adjoint of your SO8 and your 15 is the adjoint of SU4, that is fine. But there is no adjoint of SU2. Okay, so that's why SU2 cannot be there. Okay, so the embedding SO8 as SO6 cross SU2 is not allowed. Okay, as I'm saying SU4 or SO6, they're homework, if you can write it down this way. They are not allowed. Rather, it could be like 2 U1 factors as follows. So like SO8 is containing SU4 cross U1 or SO6 cross SO2, then 8 can be composed as S6, 0 plus 1, 1 plus 1 minus 1. So keeping the same thing mind as we have discussed earlier, the trace of the U1 charges, the sum of the U1 charges to be 0. And that gives you the 28 in this particular form, 15, 0 plus 1, 0 plus 6, 1 plus 6 minus 1. And this is the correct embedding. Another way of looking to 8 is 5 plus 3, so which you can realize as a 5, 1 and 1, 3. And then 20 would be 10, 1, 1, 3, and 5, 3. So S8, you can think of like SO5 cross SO3 or SP4 times SP2. Similarly, 8 could be written as a 4 plus 4, or it can be written as a 4, 2, right? So from primarily, it can be think of like SO4 cross SU2 or SC4 cross SP2. So now, if we do that, then 20 will be written as a 4 cross 4 symmetric times this 2 cross 2 antisymmetric part. And another part is 4 cross 4 antisymmetric and 2 cross 2 symmetric part, which is basically written as this particular 4 cross 4 S1 antisymmetric, 4 cross 4 antisymmetric, and this 3 is symmetric. And the adjoint of each subalgebra must be singlet of the other. But SO4 adjoint is in the antisymmetric product, which transforms as an SU2 triplet. And so it cannot be SO3, like because the SO4 adjoint is lying here, but it's accompanied by SU2 triplet, not the singlet, so that it cannot be. So that's why SO4 for SU2 is not a correct choice. On the other hand, SC4 adjoint lies in the symmetric product of its fundamental representation. Like SC4 adjoint representation lying here, but it is accompanied by the singlet of the SU2. And the symmetric product contains the singlet. Hence, we conclude that the correct embedding is SO8, say SC4 cross SC2 or SO5 cross SO3. Now, this 4 plus 4 combination can be thought of as a 4, 1 and 1, 4. Either it's like ST4 cross ST4 or SO4 and cross SO4. Again, we can write it down as a 4 cross 4 antisymmetric, 1 plus 4 cross 4 antisymmetric, and then 4, 4. With the same argument, the obvious embedding would be SO4 cross SO4 because this lies in the antisymmetric part and accompanied by the singlet of the other one. So these two tells you that this embedding would be SO4 cross SO4. Since SC4 adjoint lies in the symmetric product of its fundamental, while the SO4 adjoint is to be found in the antisymmetric product, the same argument. Now, 8 also can be treated as like a 4 plus 4, but it's like a 4 plus 4 conjugate. Then the 28 will be 15 plus 1 plus 6 plus 6. The 15 is the symmetric SC4 adjoint, and 1 signifies the presence of E1. So can you thought of like SO8 to be like SU4 cross E1? Then the 8 would be like 4, E1 charge half plus 4 bar, E1 charge minus half. So the sum of the E1 charges is 0. And the 28 would be written like in this particular form. Right? Another way of looking into SO8 is 4 plus 4, but now it is decomposed in terms of more than 2 simple algebra, like 2, 2, 1, 0 plus 1, 1, 2, 1, 2 minus 1. And the 28 is written in this particular form. The first 3 terms because they are singlet, and also the E1 charge is 0, and the 1, 1, 0 So triplets are not accompanied by the other singlet, but it's a basically triplet. Other triplets are also there. So in the adjoint of 28, it basically does not contain SU2, rather SU2 had symmetric product of two real objects. Okay. So this implies that the 8-dimensional representation is of SP8, not SU2 cube. So the correct embedding would be like SP8 is containing SU2, SU2, SU8, and so on. So this is the way we can think of the embedding and all those things. And I would suggest to look into the review article by Fransky, where there are lots of tables are given about the embedding and all those things, and that now you should be able to read and understand those aspects.